like our usual process, this recording will be on YouTube. Hello, everybody on YouTube. Hello again. I should say that. But your faces are not going to be on there, so you should be able to see my screen now. Let's see, just a moment. Let me see if I can make it so I can more easily see you all. Of course not. Okay, so when I get into lecture today, if you have a question or a comment, I don't know that I'm going to be able to see you unless you hit the raise your hand button. So just unmute yourself and ask a question if you have any questions, okay? Okay. So today, great day. Great day for some mixture models, don't you think? Why not? Anybody want to answer that? Is it every day a great day for some mixture models? Nobody's going to say that. Someone's going to at least like that, you know. But so what I did in this class is I wanted the chance to give you some of the more not advanced, but some of the models that we don't cover in other places, and mixture models are one of them. We don't often have we don't have a class that we teach on that, and every time I think about teaching it, something happens and I'm not able to do that. So mixture models are what we're doing in class today. Where they fit into multidimensional measurement models is sort of when you combine mixture models with other versions of things, in particular mixture item response models. In the early 2010s, people were really interested in mixtures, and mixture Roche models became very big. So mixture Roche models were a type of mixture IRT model. We'll get to a little bit of those coming up. Then another features about class. Your homework 4 I will be grading within the next week, so you'll hear from me about that by next Wednesday, hopefully. And there is a new homework that just was assigned, doing mixture models. So you're going to have some practice with mixture models as well, too. Mixture models are largely exploratory. Let me get this started here. That one. They are exploratory methods, generally motivated by the idea that people are trying to find groups of similarly behaving or performing observations or people. So if you have an assessment, you may want to understand which students tend to perform similarly. You may have heard of classification of mixture models prior to this, but this mixture model framework is sort of a nice model-based, likelihood-based method to go and estimate different classes of people. How many of you have heard of mixtures before, apart from those who've worked with me, of course? I got a thumbs up from Alfonso. Thanks, Alfonso. Got a couple thumbs up. Yeah, mixtures are interesting. Thanks, Sergio. Interesting things. In fact, I managed to, let me pull the chat up here. There we go. Yes, thanks, Jacinta. Yes, we've worked on a few mixture things. All of you who've worked with me probably have some mixture background. I wanted to give a little bit more formal presentation about it as we go today. So let me just dive in. Let's start there. So mixture models are the big picture topic. Latent class analysis is a type of mixture model. You may have heard both of those terms before, but think of it this way. A mixture model, or a broader class of things, is a finite mixture model. It's a set of models that are trying to determine different groups of people. That is what's being mixed in the mixture model, the mixture of different sort of groups, subgroups of people. So when you look at data, you can see different groupings. In fact, I hesitate to do this, but I'm going to. We'll see how this goes. You know how the off the cuff, on the fly lectures work, but do you remember the terrible example from class a few months ago, where we talked about Pearson's crabs data, basically the measurement of crabs, animal crabs size. Let me see if I can find it real quick. Here it is. And I'll bring this down here. So I believe I'd shown you this image. Let's see if I can make it bigger. Right here. Does this look familiar to you? A little bit? It was a bad set of jokes that came with Pearson's crabs data, but this is data from like 1890, and the green line is what Pearson had observed, and this is sort of, I think it's some measure of the length of the crab itself, some like a version of our height, right? And Pearson had sort of thought that, this green line looks like it's not really a symmetric distribution, but he sort of was thinking about data and thought that perhaps really what you have here is, instead of having one species of crab, perhaps this is sort of when you go and measure crab themselves, perhaps what you've got are multiple species. And so the thought in the mixture model sense is that you may have this one species that has this distribution, this lower distribution that you see here. Hopefully you can see my cursor moving over. And this upper distribution would be the other species. And you can tell their means are different and their variances are different. And really what happens is if you take a sample from each of these distributions, let's just say you equal numbers from each, or even inadvertently didn't realize there were different distributions of crabs, like I wouldn't understand that, the green line, the data that you observe, could have come from that. And that's the thought that Pearson had, was that if you have multiple distributions of people, when you look at data, so just the marginal observation themselves, that marginal observation could be the result of combining two different groups of people's data. So you've got this one group up here and this other group down here. Am I making any sense? Anybody have questions about that thought process? No. So as you're noting with this, there's sort of a couple things that are going into this that are not what we would call a confirmatory model. Basically, you're asking a question: do I have groups of people performing differently on my data, or in a measurement sense? Do I have different groups of people acting differently on a measurement model of some sort? And so that puts this type of methodology that we're going to talk about today, the way we're using it today, into an exploratory type of framework. But, as you know, you've heard me describe this all the way along, exploratory frameworks can also be used in confirmatory. There's sort of a blurred edges between what's confirmatory and what's exploratory. So I've reorganized sort of the topic list for what's coming up. But next week, we're going to talk about more confirmatory versions of mixtures. Those are called diagnostic classification models, and we'll talk about why we do those next week. But for today, since we're on the topic of mixtures, we're going to talk about this in an exploratory sense, understanding how many groups of people we have in our data. Sound good? Okay.
Jonathan, I have a quick question.
Hi, Nathan. I didn't say hello to you. Welcome. Please.
Thank you. So, first of all, I'm really
not a problem.
sad because IDAS and HPC is down, so I'm having stand withdrawals. So
that's right. That's right.
Crazy
that's
today.
right. It's maintenance day. That's right. Right during class, no less, right? So.
But my question is, since we're talking about like exploratory approaches, so one question that I've always had is, let's say that we are in a consulting scenario and somebody has a data set. Maybe the data set is trying to answer a question that doesn't have a lot of theory to back it up, or there's just no reason or no good details for using a confirmatory approach, because they just don't, either the details are missing or they don't have it, whatever the case is. So can you fall back on an exploratory model? Or like, what would be the solution to that? Because I agree that exploratory models kind of seem like you're throwing things to the wind a bit.
Mm-hmm.
So like, what would you do in that situation?
Can you please describe the situation one more time for me? I'm sorry.
Yeah. So like, if you have a data set and somebody wants you to estimate a model, but there's no theory or guiding principles to know how to set up the structure of the model.
Oh. I'd give them back their data and ask for more information. I think that's the challenge of almost any statistical consultant. If someone just gives you data and it says run a model and you don't know what's in the data, you're at a loss, right? You have to have some knowledge of the data and some knowledge of the structure, even for the exploratory analyses that we're talking about today, right? Cass, yes, this happens a lot with topic modeling, and Cass, I'm sorry for your experience in that. The thought being that you have to know at least some things about a model. So in a mixture model sense, there's no the key with the mixture model, tying it to class today, is if you didn't have subgroups, like the one class model is just a regular analysis model. So if we talk about mixture IRT models, well, a mixture IRT model with one group or one class is just an IRT model, right? So you need to know at least enough to know what types or what framework of modeling that you're even in before you go and start to look for this type of data, use this type of approach. Does that make sense?
Yeah, can I add, because I think, so there's a certain situation that I could see happening. So like, let's say that you want to do a mixture model, but maybe like the data that identifies which people belong to which class is confidential, or it's just like you cannot have that data, but you want to figure out like, are there distinct classes that are present, that could exist, or maybe for a fact they exist, you just don't have the data to find them.
Yeah.
Is there a way to approach that?
Well, yeah, you can, but then you don't know whether when you group somebody, that group is actually a legitimate group, or sometimes what people use the word spurious, sort of this, just a quirk of the analysis itself. For instance, one of my previous colleagues, Karen Samuelson, did a dissertation when I worked at Georgia. Karen was there. Did her dissertation on mixture IRT models, and she used them to understand if there was diff present for the latent groups of people. So basically looking at items, not having a group mechanism per person, and seeing if there was a group difference in item parameters using the groups that she found with the mixture model itself. That seems to be good on the surface, but the problem is, like any exploratory model, mixture models are fraught with danger, right? And many times those groups are meaningless. And I'll talk a little bit about that as we go forward. So.
Yeah, I could see like if there's another underlying mechanism that's causing the groups to happen, you don't know if it's because they might be in like a testing situation, like are they part of a minority group, or is there some other reason that's grouping them into those clusters?
Yeah, well, there's a big methodological reason. By methodological, I mean what we do with modeling, and that is your model doesn't fit the data, right? So if you take a one class model and apply it to data, if the model isn't appropriate for it, like for instance, let's imagine you have multidimensional IRT data, but you fit a one-dimensional IRT model to it, and then you want to make that a mixture model, make it two classes or three classes of people. If that first class model doesn't account for the multiple dimensions, the only remedy this framework has is to add classes of people to make it fit better. And when you do that, those classes may or may not exist, or may not exist in the way that you think they do. So mixture models, exploratory mixture models, are, to me, not the best idea. But the framework of mixture modeling gets used a lot and can be used for a lot of reasons. So you can turn a multiple group measurement model into a mixture model and classify people into group based on it. Things like that, right? You can use these types of models for classification, or you can put a ton of constraints on them and use them for psychometrics. That's what a diagnostic model is. But for the cases where it sounds the most appealing to a lot of researchers is, I've got subgroups in my data, I don't know what they are. I honestly don't think these are really good for it. Yes, they'll give you those, but then you have to believe that they're true, and I have a hard time believing that they're true. I'll tell you more about that at the end of class, okay?
Thank you.
Thank you. All right, other questions? All right, diving in. I actually have slides today. We're going to talk a little bit. So the way I've structured this lecture, I'm starting with a very specific type of mixture model called a latent class model. A latent class model is kind of like an IRT model in the sense that it describes a very specific type of data that it was applying a mixture to, and then a very specific set of assumptions. But latent class analysis uses the most basic data, which is binary data, and uses the most basic type of model, which is an item difficulty, basically the probability someone answers an item correctly based on the group they're in. But because they're simple, it provides a nice, simple, I shouldn't say simple. Nothing is simple in what we do. Nothing is simple in this class. But because they're somewhat smaller in terms of parameters, I find that they're a lot easier to understand and a good starting point. So I'm going to teach you the latent class analysis type, and then we're going to generalize it to the mixture model. And from the mixture model, you can actually go a different direction. I will note that this is a typo on my slide. I don't know why I left it on there. I didn't go back and fix it. We're not going to do latent profile analysis, but we'll talk about model parameters now. Okay, I just keep popping up to look at the Zoom. My setup in here is not ideal, but it's going to work. But if you have a question, just, again, jump in. All right, let's talk a little bit about clusters versus classes. Actually, give me just a moment. Let me do... Nope. Hang on here. Sorry about that. You don't need to see me blowing my nose. Pardon me for that. But you may have heard cluster analysis as a technique. You may have heard latent classes before. You may also heard the term classification. Heck, ChatGPT is a classification model, right? A bunch of classifications going on. Generally speaking, you hear about mixture models when we talk about classes, but the classes that are formed by it are no different than you'd see in other clustering techniques. So often when a researcher will mention to you they're going to be using a cluster analysis, they might be referring to k-means clustering or discriminant analysis. That's kind of old. There was a field of psychology by Paul Meehl from Minnesota many years ago named taxometrics, which was trying to combine classification and continuous things. But much less often you hear latent class analysis included in that group. But it's also useful for looking for different clusters of observations. So we're going to consider the word clustering and latent classes to be the same for today. There are some cases where people make a little bit of a definition, like the way we talk about it with machine learning these days. If you have a fully unsupervised machine learning model, that would be clustering, figuring out what the clusters are, whereas if you were to go and try to take the result of that and put people into those clusters, that's now classification. I don't want to get into it. Let's just think we have a bunch of data. There's a grouping variable that's hidden that we didn't observe. We're going to try to figure out what that grouping variable is. Sound good? I don't know why I'm asking you that. I'll take it. Take your word for it. How's that sound? All right. So although I'm going to use the terms classes and clusters synonymously, this general approach of latent class analysis differs from some of the methods that I just mentioned on the previous slide. In particular, latent class analysis is model-based. Literally, you have to define a statistical model for one class and then generalize that across the classes that you're using. The other methods on this other previous slide, like k-means, clustering, or discriminant analysis, it's much less defined what the statistical model happens to be, although actually in both of those it's there, it's just not talked about a lot. So by being model-based, what we're doing is making very explicit assumptions about the data that we have. But those are assumptions that can be tested, so I think that's a good thing. This is the part where I've mentioned this story before. Many of you who work with me probably have heard it too much, but when I was in grad school, I took a class, an advanced stat class, and they provided data for us. This professor, who was a good professor, just gave us a set of data that was a bunch of like heights of individuals. They said, "Oh, these are the heights of students in my intro stat class. What I want from you I want you to tell me the mean height for men and the mean height for women. Oh, but I didn't actually write down if a person was a man or a woman, right? And so that's a setup for a mixture model, right? You have to come up with, and so based on that, you have to make some assumptions. What's the distribution of height like? And does the mean, like, so for instance, you might say, well, I've got a normal distribution. Maybe there's The height for men, the height for women both follow normal distributions, but the distributions may vary in their mean and they may vary in their variance, right? That's the setup that we're talking about here. But that question, that assumption about being normal, that's one thing we can test. About the different types of parameters we need, that's other things that we can test as well too. All right? All right. Diving in. Latent class analysis. 1968 was a good year for some books that we all talk about. The Lord and Novick book came out in 1968, but also another book from Lazarsfeld and Henry came out, and that Lazarsfeld and Henry book covered latent class analysis. I believe the title was Latent Structure Analysis. So here, basically, what we're doing in a latent class analysis parallels the exploratory work that we've been doing in class, right? In the data sets that we've had in class, like homework 4, you were trying to determine how many dimensions you have in your data, and then to a lesser extent, what those dimensions actually mean. In latent class analysis, we're trying to determine how many groups we have in our data, the number of classes. And then once you figure out how many classes you have, you try to figure out what each class represents. So you don't know the final number of classes before you start with this exploratory process. And you can see the parallel, right? Number of factors, number of classes. Turns out there's a huge parallel between these types of models, although maybe not specifically latent class analysis, this type of model, and what we do in latent variable model, continuous latent variable models. So not just the modeling architecture setup, but there's some mathematical parallels, which I won't cover now, but you can find in the literature as well, too. This sort of C equivalence classes of when latent class models are sort of the same as some of our other psychometric models. So you don't know how many classes you have in your data, so you have to determine that. We determine that through posterior fit statistics. We also don't know what each class represents, so we have to figure that out. So if we're talking specifically about latent class analysis, now remember, mixture models, that's the big umbrella. Finite mixture model, some people describe that. Big umbrella. One narrow sliver, one type of that is a latent class model. And specifically, the latent class model assumes that we have data that are binary outcome data. So 0, 1 values. So you can think of test items or true-false questions, anything with two outcomes, right? What we will then try to do is we will estimate a series of models with a differing number of classes. For each class, we're going to estimate the probability that each variable is equal to 1, right? So basically, within a class, latent class analysis model is simply each item gets its mean, or its item difficulty, or the probability equals 1. Remember, probability of binary item equals 1 is what we would call a classical item difficulty, right? The proportion of people who answer correctly. What we're doing here with latent class analysis is estimating a class-specific item difficulty for each item and each class. So we'll start with, let's say, a one-group model. Each class has, we have a set of items. Each class has a problem. That one group has one item difficulty. Sure enough, it will be our item difficulty in our data. When we go to 2, now each class, if we have 10 items, there'll be 20 item parameters, right? 10 item difficulties for one class, 10 item difficulties for another class. There will also be a probability a person falls into each class as well. So let me just put this onto the slide. So we're estimating for each class a class-specific item difficulty parameter, that is the estimate of the probability each variable is equal to 1. We will also estimate a base rate, basically the proportion of people who fall into each class. Like this, we could be thought of as a prior distribution. Alternatively, in a mixture model sense, this is actually the structural model. So we talked a little bit about structural versus measurement models before, right? Measurement models being where latent variables where the latent variable and the data meet, right? That's measurement. And then structural models are often talked about by like distributional characteristics. So when we thought of an IRT model, the measurement model was the item response part. The structural model might have been the covariance matrix of the factors, right? So for a mixture model, the measurement model part are the item parameters themselves. The structural model part is this base rate probability that each observation falls into each class. Now, I will note that the mixture model process, if you've seen a k-means clustering before, what ends up happening is the same type of process. You say, oh, I think there's k being the number of classes. I think I have 2 classes. Well, what k-means will do is try to go and figure out, again, the mean for each variable, which in our case is the probability of variable equals 1. But the way it goes about doing that is it assigns observations to classes with certainty, right? Basically, a person's class that they go into in a k-means analysis is the closest in a statistical sense to the mean of that class. So what do I mean by that? Right? If you have a class and you have a bunch of means of variables, you're trying to tell how far a person's data are from those means of the variable statistically, and they use multivariate normal distribution usually to figure out the means of variables, and then use something called the Mahalanobis distance to sort of statistically weight each person by how far they are from each class. In latent class analysis, though, we do not each person does not get put into one class with complete certainty. We're actually estimating the probability a person falls into each class, and that's a probability, right? So it could be the case that we have some people who are 75% chance of being in class 1, 25% chance of being in class 2. So this probability that we estimate at large for any one person falling in any class is like a weighted average of all the people in each class's probability. So, how am I doing?
I have a question, Jonathan.
Yes.
A quick one.
Yes, please.
So, you said that every personal observation has some kind of prior probability or prior distribution.
Yeah.
Of being assigned to each class.
That's right. We have this is sort of like an empirical Bayes model in that we are going to estimate a probability that a person at large, before we observe any of their data, falls into one of the classes that we have overall. So yes, that is what the structural model is, and it does function like a prior probability.
Oh, great. So is that a number or is that an assumption?
That is a number. I mean, that is a point estimate. We of course are assuming that the model is correct to be able to use it, right? If the model is incorrect, that number is going to be very far off, most likely. But it is something that we will be able to estimate and to use as we go forward. Does that help?
Yes, great. So but is that based on the responses or the information we have for the person?
Yes. I'm laughing because it's let me get to the model part and I'll show you what it's based on, okay?
Okay.
Also, in the reading for this week, there's a book, Chapter 6 by Bartholomew Knott and Mustaki. What you'll find is basically the model parameter for the probability, the model parameters for the probabilities are, yes, they are basically taking each person's probabilities, which come from their item responses, right? And the model parameters themselves. And then using those as if they were known to come up with the probability at large. So it is kind of like a prior distribution. Hope that helps a little bit. Ahmed, do you have a question?
Yeah, for the assumptions for classes, as the example that you mentioned, the heights of men and women.
Mm-hmm.
So prior fitting the model, we have to set like a mean for men height and women height.
No.
I mean,
no. What we
okay.
need to set is the distributional form for the height of men and for the height of women. So what I mean by that is, we just need to know what one group's distribution is, and then we attempt to estimate the parameters of that distribution. So in this case, if we assume both followed a normal distribution, we would try to estimate the mean for men and the mean for women, and we would try to estimate the variance for men and the variance for women as well too. So basically, it's like saying I have a bunch of different models on my data. You could also think of what we're doing as in the normal case, in the case where like this idea of the heights. That is almost equivalent to a heteroscedastic two-group analysis of variance, right? If you think about it, if you knew who men were and you knew who women were, this is an ANOVA model. You dummy code, the sex of the person, and you predict the mean with that. And then usually in that ANOVA model, we estimate a common variance, but here we could go and estimate separate variances. That's like taking the variance, converting it to a location and scale type model, and estimating that as well. So interestingly, like these are very interesting canvases of models, but we are trying to estimate all the model parameters themselves as much as possible. So there's very little speculation. I hope that helps a little bit.
Yeah, but if we assume that they both follow the normal distribution, so we have to set a mean for each class in this case. So, for example, if we believe that men average is taller than women or higher than women, so how can we assign this in the assumption that we set for each class?
So we can actually assign that. We can actually assign that one class's mean is greater than another. We can put constraints on it as well. But the trick in this is to form a proper probability distribution for each observation. So if you think about what you've learned in this class about maximum likelihood, right? We had to build a likelihood function, and we started with each observation's function, and then we went and built it for the sample, and then based on the sample, we were able to go and plug that into like an optimizer. In what we do, the latent class model has another probability density for an observation. That density, though, is a mixture of the two distributions, but it still integrates and sums to one, so it's proper probability density. So all the parameters that are in that, so long as that the model is identified within one class, are able to be estimated in a maximum likelihood estimate type framework as well, too. So we don't have to set anything. What we can set, and actually in that homework assignment I told you about, the professor did say you can assume, actually, I believe he said you could assume the variances were equal and you could assume the height for men is higher than the height for women. But that would become a two-group mixture model where the means are different but the variances are identical and one mean is greater than the other. So, hope that makes sense.
Thank you.
Thank you. Jacinta, I see you have your hand raised. What's up?
Hi. Yeah, so I am thinking about the amount men versus amount of women. So does the model assume that they are of equal size, or
No.
like I'm just wondering if it works the same, like if his class is more men than women, would it find that, or yeah, I don't know.
No, technically the model is actually going to try to estimate the proportion of people in each class. So no, you can have unequal sample sizes altogether. That class probability parameter is what that proportion represents. Again, I haven't put the equation up yet, and I always feel it's hard to point to what that parameter is without showing it in mathematical form, but let's just talk about it conceptually. But if you had 95% men in one class and 5% women in another, what you should see, if that mixture is picking up on the group or the sex of the person, you should see a probability of 0.95 for class one of the classes and probability of 0.05 for the other. You should be able to estimate it. Now, I will say there is one catch with that, though. If you don't know what proportion of people is in each group, and you end up getting a group that has a very small proportion, it's like trying to estimate a model with a sample size that's really tiny, right? So if we had, this was the data, this example I told you about from my stat professor, I think we had like 150 observations. If it turned out that 95% of those were men, right, we'd be trying to estimate a mean and variance with just a handful of women, if you think about it, right? Like that report, like 5% of 150, whatever that is, like 7.5. Good luck, right? So you can see one of the problems inherent in these models by not knowing what proportion of people are in each class. We could inadvertently run into what I would call empirical under-identification, meaning we just don't have enough data to figure out estimates. And those of you who've worked with me and who've estimated these before, sometimes you start to see estimates of model parameters that, like the standard errors get super huge, or the model parameters themselves, like you might have an item difficulty that looks like -15 or something like that. And that usually happens in cases where the class itself doesn't have a lot of people, and the overall sample size, that proportion of that sample size is really the effective sample size for the class. I hope that.
Okay, yeah, my thought came from, I know with height it probably wouldn't matter, but you know, now people are saying like men versus women versus non-binary. And
Right,
so it's
yes,
like, okay,
absolutely.
that non-binary would be a really small amount, I'm guessing. And so that's where my thought came from was, okay, would it be able to parse out that third class? Maybe it would be so under-identified that it wouldn't.
That's exactly it, yeah.
That's where my thought came from when this...
That's a good thought. And actually, let me just back up some context for it. Like I was in the stat class, like I think in 2002, so the ideas of non-binary when it comes to sex were there, but weren't as widely talked about as they are now. So that assignment wouldn't have been. This literally was the assignment: men versus women. But yes, if we put it into the modern context, where we talk about sex again, male, female, non-binary, whatever you want to classify apart from male and female, whatever people identify themselves happen to be. Yes, that would be one of the challenges: is trying to figure out what their parameters would be in the class itself, because now and that also presents issues, right? So anyway, I would actually go with, I think I probably should have introduced this example as chromosomal sex. So like if you look at your sex chromosomes, but even then that's problematic because we're used to X and X and we're used to X and Y, but if, remember in biology class there were a few odder combinations like XXY or something like that, or maybe there was anyway, there's other permutations of sex chromosomes that happen anyway. So I'm trying to figure out a way to fit this in the framework, but for the two...
Yeah, no, it's a good example. That just is what led to me thinking.
No, that's really a great question,
Okay.
and I don't, for those of you who first of all, I'm a supporter of anybody who, however you want to identify with gender, so I don't want to bring that into our class, but maybe I should have changed that example, but it was part of my history, so that's where this example came from. But yes, a very good question. There I am apologizing for what I'm doing. Other questions that you might have? All right, moving forward. So how do we estimate these models? Well, again, in k-means, I keep talking about k-means because a lot of people may have had it. If you haven't had that before, then just ignore what I'm about to say. Basically, what we do forget k-means. Let's talk about latent class analysis. In latent class analysis, we use basically distributional assumptions to determine which class a person is in, right? So I'm going to keep using this binary gender idea, binary sex idea, just to keep going since I've said it. Before, since I've just already described it. But basically, if we look at a person's height, right, that's the data we had in this example I'm talking about. We may have at a current value of our, remember, in an iterative estimation, we have different iterations, but each iteration has a set of parameters, right? So let's envision what happens when we step into an iteration and we know the mean height for males is, we'll call it mu1, and the mean height for females is mu2, right? And we have a variance, maybe a pooled variance between the two. What we end up doing is taking a likelihood with each class, right? So what's the likelihood that a person's height was part of the male height distribution, right? So we get the height of that, the peak of it on the PDF. What's the height of the women's height? What is the likelihood of the woman's height? Of that person's height being from the woman's height distribution, right? So we get a height on that PDF. And those likelihoods themselves form the basis of probabilistically, which class a person gets assigned to. In fact, that probability, a person's posterior probability of being assigned to a class, is that class's specific likelihood divided by the likelihood summed across all of the classes, right? So what we're actually doing is trying out, basically taking each observation. We may have our model parameters held constant, right? So at that, for that one iteration, we try out each class for each person, and we come up with the probability based on weighting each class's likelihood by the total likelihood across all classes. That is, that likelihood itself is like a distance. It's actually a measure of similarity. Like the higher it gets, the more similar you are to each distribution. Pardon me. So that is how estimation works. Another side note on estimation, and maybe this is fitting. I know, Nathan, you're sad because you don't have Stan with IDAS right now today. Don't worry, it's coming back soon, though. But mixture models are really difficult to estimate in Bayes settings. So often what we'll see is an EM algorithm or marginal maximum likelihood. They're actually difficult to estimate in those settings as well, too. I'm getting ahead of myself, but I'll tell you a little bit more about that as we get later in class. Okay? Okay. So let's talk about these distributional assumptions in latent class analysis. So again, just for today and just for latent class analysis, we have binary outcome variables. Right? So, you know ahead of time, our favorite binary data distribution happens to be Bernoulli, right? So, we are going to assume for a person that each variable follows a Bernoulli distribution. So here, if you have a variable, a person P and a variable I, their distribution or probability mass function, or PDF, it's a categorical version of a probability density function, is equal to an item difficulty for that item, raised to whether or not they answered the item correctly, and then 1 minus the item difficulty raised to whether they answered the item incorrectly. Right? This is educational items. We talk about item difficulty, correct, incorrect. So everybody's data follows a Bernoulli distribution, and regardless of which class you're in, there's still going to be that distribution for each data. The other key piece that we put together with this is that the Bernoulli probabilities are independent, meaning this is the same assumption that we have in IRT or in factor analysis and most of our latent variable models. We assume some type of local independence or conditional independence. You've heard of that before. So here, what that means is within each class, we're going to have a product of Bernoulli variables representing a person's data. And I have a few slides I've made these slides for a different purpose, but let's just imagine, I think this weekend we played Northwestern, not Northwestern, Iowa being we. So let's imagine Iowa has an 87% chance of winning the game. Then our distribution function looks like this. If Iowa wins, the height is 0.87, and if Iowa loses, the height is 0.13. So that's our distribution and how the likelihoods work. Similarly, actually this is it right here. This is where the likelihood comes in to play. That's just showing you the likelihood and feature. Basically, actually this should be a 0 right there. Pardon me. In the case of discrete outcome variables, this likelihood is synonymous with the probability of the event occurring, right? So if Iowa were to win, the likelihood of them winning was 0.87. Well, that was what we had somehow known earlier. Now, let's talk about independent variables. Let's imagine that I just picked a game, Michigan versus Ohio State. That's always a famous one in the Big Ten. Of course, football, but it could be any other sport. But let's imagine Michigan has a 57% chance of winning. By the way, if you're not into sports, you don't have to worry about this. Just think of this as answering item 1 or answering item 2. What's the chance that Iowa wins and Michigan wins? That's what this looks like. Here, that's the product of those probabilities by independence. And that's really what I'm getting at here. The idea of local independence forms this function down here. We take, for each item, our Bernoulli variable, and we multiply those probabilities together to get a joint likelihood function for each class. Does that make sense? Somewhat?
Yes, I have a quick question.
Yes, Vladimir. Mm-hmm.
Yes, this is for related to each class, or is for each observation or subject within that class?
Okay, so this right here isn't there yet. I'm sort of building toward our model function. So give me just a second, and I'll show you a little bit better. Does that sound okay?
Yeah, thank you, Jonathan.
Yeah, thank you. By the way, to be a little bit better at the answer, not just to procrastinate on answering your question, this will be the function within each class for a person, right? It'll just be another slide.
Great.
So finite mixture models look like this. Overall, I mentioned before, latent class models are special cases of finite mixture models. So again, big umbrella finite mixture model, right? Small, narrow type of finite mixture model is a latent class model. So here, let's imagine we have a vector of outcome variables. We can just describe this as a vector for one person. I didn't put a person subscript on it. But the distribution of the data for a person is said to come from a very familiar form, which is this. We sum across all the classes a person's class-specific likelihood. That's what this f of y given c is right here. So conditional on class C, what's the likelihood of person y's, or the data in y for this person? Now, we know this distribution has to be a normal, or not normal, not a normal family, but a typical distribution function in that it either integrates to 1 or it sums to 1. That is what it has to be. So for f of y, the marginal distribution, to also be a proper probability distribution, we have to weight each probability, each class-specific probability or likelihood by a mixing proportion. That's what eta c happens to be. This is the proportion of people in each class. And this n-looking parameter I'm going to call eta. I hope that's correct. I think it is. So, again, this is where the term mixture comes from, because basically, if we think about it, we have a set of distributions, one for each class, defined by this function in pink right here. But to get to a person's observed data, we have to go and weight each chance that they're in each class by the base rate probability, the proportion of people in each class. And so this is our general latent class or finite mixture model likelihood. The functional form of what the class-specific likelihood happens to be varies by the class of model, but this is where your model will go, right? If we have a mixture IRT model, f of y given c is an IRT model, but with each parameter relative to class C, right? Not the C parameter like guessing, but C as in class C here. How are we doing with this? Any questions so far?
So is it mixture because we are combining people and classes?
It's because we're basically for a person, we're saying the data that we observe is a mixture of distributions they may have come from. So we are combining class-specific distributions, mixing them together, if you will.
Awesome. Thank you.
Thank you.
Yeah.
Yeah, and this eta c, again, this is the proportion of people in each class. It goes by a lot of different words. If you're in the mixture model world, sometimes we call this a mixing proportion. It's literally how much of this distribution is added to how much of that distribution, right? In other features, in other frameworks, we might call this a base rate probability. In other languages, we might call this a prior probability, right? Basically, for each person, before we collect their data, we know the probability they're in each class. It's this probability. And then once we collect their data, we can update it, and now they'll have a posterior probability for each class. So in many ways, this is like what we would call a Bayesian model, although I would call it an empirical Bayesian model, because the class-specific parameter for each person is this thing. Actually, it's not this thing. It's a categorical distribution. They have a chance of being in each class. So if we're putting this in a latent variable framework, right? If you have a unidimensional IRT model, there's one latent variable. It follows a normal distribution almost always, right? If you have a latent class model, there's one latent variable, but it doesn't follow a normal distribution. It actually follows a categorical distribution. So it's this odd modeling framework that's sort of parallel to what we're used to in the continuous latent variable models, but it can be very helpful in different places, and it certainly acts and it behaves in weird ways compared to what we're used to. But questions on any of this? Other questions, I should say. In the absence of questions, we roll on. So, previous slide, finite mixture model, the big umbrella. This slide is a latent class analysis. Right? So basically the difference between the last slide and this slide is highlighted in pink. This is our class-specific joint likelihood, right? Where each variable follows a Bernoulli distribution, and they're assumed to be independent conditional on class, meaning that, so for a given class, this whole likelihood, this probability, basically that we get from each item, gets multiplied together for each person. Did I see a question, Ahmed? I don't think I did, maybe. You have a question?
Oh, thank you.
Yeah.
I'm just No, it just joined the meeting.
I'm sorry? Did you have a question, Ahmed?
Sorry, my internet broke down, so I just.
Oh, no problem. No problem. Sorry about that.
No, thank you.
I'm over here. I'm doing my best.
Yeah.
I'm like, come on, someone bail me out with a question, please. I'm struggling here. But no. Let's keep going on. So again, what does this mean? It means basically when we get a person's data, and actually this should be a P here, Y sub P. We basically go and estimate a likelihood that they're in each class. That's what is in pink here. And then weight that likelihood by our estimate of the proportion of people in each class, A to C. Right? So this is the likelihood function. This is what drives the estimation process. And you can tell right now we have a set of model parameters. And again, going back into things, the term in pink here, the class-specific likelihood function, is really a class-specific model. So these are basically our measurement model parameters, right? You can see we have our data, and we have something to do with this class, pi IC. That's the measurement model. So we'll have a set of item difficulties for each class. So we'll be able to tell whether an item's hard or less hard for it. Nathan asks, is A to C a simplex? I hate the term simplex because it's ill-defined in many places, but A to C sums to 1. So I would say it's ipsative. Maybe in the Stan user model they call it a simplex or a softmax or something like that, but I don't like using that term. Does that work, Nathan? Thank you. But yeah, it sums to 1. All right. So let's talk a little bit about local independence, right? In latent class analysis, all the items are independent, conditional, and class. You think that's a good idea? I don't know. Any model conjecture may or may not be a good idea depending on your data. Let's talk a little bit more about where it comes from. We use local independence in IRT. We use it in factor analysis when we have uncorrelated errors. And the nice thing about local independence is that it basically tells us that the reason why variables, we may observe correlation in variables marginally, is due specifically to the latent variable model itself, right? So remember, local independence is describing that, given a class in this framework, or given a latent variable in the IRT framework, given a theta, that the items are independent, so the probabilities multiply. Another way of putting it into more understandable terms, like that mathematical convention means little. I want to remind you of basic statistics. I feel like I talk about basic statistics a lot, but I'm talking about them some more here. Do you remember in basic statistics, we sometimes when we talked about the idea of correlation, so you may have a variable x and a variable y, and they are correlated. Do you remember we talked about there are like at least 3 ways why the correlation may be present, right? We talked about x may cause or predict y, right? So that may cause a correlation, or y may cause or predict x. Or the third way, which was z, a variable we didn't observe, causes both x and y, such that if we were to condition on z, x and y might be independent, right? Conditional distribution of x given z is independent of the conditional distribution of y given z. Well, that's local independence, right? Basically, we're saying we take a bunch of items. Those items may have some type of relationship. In binary items, we talked about tetrachoric correlation being one of those measures. Why are they correlated? Well, we're trying to estimate why, and this model is hypothesizing that why they're correlated is because people show up in latent classes, and that if we knew the latent class of a person, we'd have uncorrelated data, basically, within that class. So local independence, very strong assumption, but also is a very hallmark assumption of psychometrics. Another way that we talk about it in factor analysis and in IRT, but in factor analysis is a little bit easier, because in factor analysis you can sort of violate a local independence by easily adding model parameters. You can do the same in IRT, but IRT makes it a little bit more difficult. But basically, when we go and say we have local independence in a factor analysis or an IRT model, what we're saying is the reason why the observation, reason why person's responses may correlate across the data, or why variables may be correlated, is because they're all related to this latent variable, this factor that we're trying to estimate, right? And furthermore, if we, let's say in factor analysis, add an uncorrelated residual, where we basically violated local independence, then what we'd have to say about it weakens our validity argument about the factor itself, because what we would be able to say if local independence held was that the factor was the reason why variables are correlated, right? So basically the factor, or people's individual differences on the trait, induce this correlation in the variables. But if we don't have local independence holding, if we add an uncorrelated residual, that's like weakening that factor argument. Basically the factor and whatever the uncorrelated error happens to represent now cause this. So basically it's the factor and other things, or factor and stuff. So local independence is a fundamental assumption in psychometrics. It's also a fundamental assumption here in latent class analysis. How are we with local independence? You like it? I get a thumbs up. Thanks, Vladimir. Thanks, Alfonso. We're good. Yeah. All right. So let's talk about estimation. Successfully applying one of these models involves resolution of two questions. Number one, how many classes do we have, and what does each class represent? So number two is dependent on number one. We have to figure out how many classes are present first. And the answer to how we figure out number of classes is, I believe I would call this brute force. We are going to estimate separate models, increasing the number of classes. Hey, that homework 4, you estimated separate models, increasing the number of factors, right? Don't remind you, right? I get it. Yesterday was Halloween. It was scary for a number of reasons, including homework 4. So here, we are basically doing the same approach. And we're going to estimate multiple models. Once we decide which model is the best, right? And I'm going to define how we decide that in just a moment. It's not really all that impressive, but we do it that way anyway. But once we define what our best fitting model is, we have to then go back and inspect the item parameters to determine what each class represents. Okay? And this again parallels EFA almost entirely. Exploratory measures. So where do we estimate this stuff from? I'm going to use exclusively M+, and I'd recommend that you do also. There are R packages. There's a SAS Proc LCA. There's Latent Gold. But M+ is what I will use, and since we all have access to it with Aptainer on Argon, although not today, hopefully tomorrow, we'll use M+ for everything that we do. One thing I will note in terms of the estimation difficulties, why these models are difficult to estimate, is that unlike the models that you've estimated at this point, these models do not have a single peak in their likelihood function. So, little did you know, prior to this, the CFA models, the IRT models, everything that we've run in this class to this point, I don't believe we fit a 3PL model. 3PL is not part of this, but the 2PL IRT models and our factor analysis models are guaranteed to have a single maximum in their likelihood function. The reason for that is they fall under something a broader class of models called an exponential family. There's great statistical work that showed that underestimation with maximum likelihood, or the likelihood function for exponential family models, is single peaked. There's one. What that means in estimation, if there's a single peak, remember how the estimation process works. It iterates to try to find that peak. It sort of inches its way up a mountain to find it. Well, with the single peak, you'll find that. That's how it works. But when you have more than one peak, right? And not only that, not just more than one peak, there may be a single maximum peak, but the likelihood function is not smooth. There's multiple sort of local minimum, what we call local optimum, right? In addition to a global optimum. So what happens in a likelihood estimation sense is we start by randomly selecting starting values for our item parameters and maybe our structural model or class mixing proportions. That puts us into one area, and what the algorithm will do is find its way to the peak that's closest to that area. But that may not be the global peak. So what we have to do in maximum likelihood is we have to estimate for each model more than one time, basically to try to show us converging evidence that the maximum that we found every time or is actually found more than once, trying to get us to understand that. But this actually happens to be a huge problem in Bayesian estimation, because in Bayesian estimation, the same function will happen, the same feature will happen. You'll randomly start and you'll move up to a peak, basically of a posterior distribution, but sometimes you may end up flipping the signs, or sometimes what we call, in Bayesian estimation, we have multiple modes we have to worry about, and multiple peaks. But we also have to worry about something called sign or label switching, meaning because this is an exploratory model, class 1 and class 2, if I estimate this model with my starting values, I may get class 1 and class 2's parameters, right? Think of 5-item difficulties for each, let's say. And then you go and estimate this, 2 classes, and you see that your item parameters for class 2 are identical to my item parameters for class 1, right? And your item parameters for class 1 are identical to my item parameters for class 2. And you look at our likelihoods, the log likelihoods, and they're identical. What happened was the labels switched. They permuted themselves, right? So that happens also. Sort of chaos in many ways compared to what you're used to. These models they will throw you for a loop in estimation, but it's a good loop. It's a challenge that'll teach you a lot about estimation and working with these things. So estimation is difficult, yet again. Questions on any of this so far? No questions. Keep moving.
Yes.
Oh,
one.
Vladimir. Yes, please.
Sorry, yeah. But what's the meaning of those multiple peaks? We will have more than one in our ML function, but what's the meaning of that? Why is that happening there?
The likelihood surface itself is just built. There's no guarantee of it. The model itself is not in a class of or a family of likelihoods where we can easily describe what it looks like. And what that just means is that there's sort of ridges or valleys or it's hard to describe because it's this multidimensional like surface that we're trying to figure out where the maximum is. But generally speaking, it's just a bumpy surface that we're trying to go and figure out where the global maximum is. That causes all sorts of issues estimation wise. I hope that answers your question a little bit.
Yes, that's something. Thank you.
Thank you very much. All right, let's start with an example. This example came from this Bartholomew Knott and actually Mustaki book. And these are the data. I don't know if I can see if I can zoom in. Nope, I cannot zoom in. Sorry, guys. But here's your data. Let's see if I can. Nope, that's not it. There we go. These are the data right here. This paper was 1977 by a couple of professors who used to work at University of Maryland, George McCready and Chan Dayton. And they had a 4-item assessment. This was like a math test, I believe. And they collected 142 observations, and this is the count of different observations. So with 4 items, 4 binary items, there's 2 to the 4th power, or 16 different response patterns, right? So here are the 16 response patterns, and here's the number of students they observed with each response pattern, right? So here, 41 students didn't answer any question correctly. That was the most frequent response pattern. With me so far? So now, of course, no, don't do that, Zoom. My Zoom window's in the way of me using my Quarto. There we go. All right, get out of here. There we go. So now, what they decided, this is in the fairly early days of latent class analysis. Back in the 1970s, it was really, really difficult to estimate these models. I just mentioned today that it's hard to estimate these models, but think about this, 50 years ago. It was even harder, right? But here, we've got our 4-item test. McCready and Dayton really wanted to look for 2 groups of people. They had looked for students who had mastered the material. Now, the word mastery is, we're going to come back to that next week. What does mastery mean? Mastery is arbitrary. What does it mean to master something? Right? Am I a master of psychometrics? I don't think so, right? I get a lot of things wrong. But then again, I've spent 20 years in the field. I should know something. I'm not quite entirely sure what mastery is. But that's what they're hypothesizing. They're looking for two groups of students. Those who had mastered the material, those who had not. This is a little bit backwards from our previous approach of the exploratory process, but this is the paper that they started with. By the way, I would argue that this paper was probably the very first diagnostic model paper that was published, because this idea of mastery versus not started the whole new set of literature that became what we talk about with diagnostic models now. So, now, because we only have 4 items, we really can't do the exploratory approach where we fit 2 or 3 or 4 classes. We're just going to fit a 2-class model here. But let's just pretend that that's what we end up getting. And this is our M plus input. All right? So in M plus, there usually is a model statement. I didn't spend a lot of time talking about M plus here. But in the absence of a model statement, by the way, this latent class analysis of McCready and Dayton's data, this is actually one of the example data sets that comes with M+, and it's in their user's guide. So you can figure out, like, it's that classic of a data set in this sense here. And they use it for the latent class analysis. And basically, here, normally what I do when I look at files like this, like M+ files, let me grab the M+ file here. I like to look for the model statement. There's no model statement. If I were to put a model statement in, it would look like this. And this is where, let me go through what we have here. Here, we have to tell it the data set. I have this mddata.dat. You can find it on our GitHub site. Then we have to tell it what variable names are in it. Remember, M+ data, we actually don't import column names, because M+ is weird like that. So we have variables U1 through U4. We tell it how many classes we want to estimate. In this case, there's 2 classes. And we go and tell it that the items are categorical, which means it's looking to categorize them as binary or, in our case, discrete data, not continuous. If we didn't put categorical in, they will treat them as continuous and use a normal distribution. When we use categories and we only have 2 categories in our data, it'll be binary. Under mixture, we have to, under analysis, the analysis section, we have to tell it the type is mixture. If we don't tell it the type of mixture model, it won't understand this classes line above us. And this starts option is the part that tries to circumvent the multi-modes, the multiple peaks in the likelihood function. Basically, we're going to run, for a 2-class model, we're going to estimate this 100 times. And we're doing 100 times to see how many of that 100, those 100 times that we estimated it, end up in the maximum, the highest likelihood. Now, the 2 numbers that show up after start, the first number is how many times it wants to start the estimation process. So what it will do is try 100, and the last number is how many of those 100 you want to move to completion. In that, if you have a bigger number to start, but a smaller number at the end, it just completes the ones that have the highest likelihood in the intermediate step. I don't like doing that. If I'm going to start it, I'm going to run all 100. So starts 100, 100. When I run mixture models, I tend to have the same number show up both on the output of it. We're also going to output some statistics, Tech 1 and Tech 10. I'll talk about those in just a bit. And to plot things, we can plot variables this way. But here, this is where the model itself, if we were to form the model, it would look something like this. Overall, in the model statement, you can put an overall model in. Now, this is your model across all the classes. But then you may need to describe class 1. So in this case, because I describe class 1, I describe my label for my classes as starting with C, my class 1 model would show up in syntax that looks like this. Percent, then C, this lowercase c right here is the same C that starts my classes. It's my name for it. And then #1 or #1 means it's the first value of the class right there. Now here, what we could end up doing is listing all 4 of our items, but in our case, what we're estimating is just the item difficulty, or an M plus sense it estimates the item, the threshold parameter. So here we could actually put U1 $1 to U4 $1 in our syntax. And for class 2, similarly, we may have the same model. So let me describe to you what's happening here. What this is doing is it's estimating 4 separate thresholds in class 1 and 4 separate thresholds in class 2. And overall, there's no difference in model. So that's how the syntax is being built. When you build your own model in M+, you put overall in, but then for each class specifically, you give it your distinctive model. So for instance, in homework, I'm having you estimate this model, but I'm also having you estimate a mixture IRT model, mixture 2PL. The 2PL syntax will show up in both of these set parts for each, or actually in each class. And it's important to think about that, because when you put a set of a model within each class statement, so like here under class 1 and here under class 2, what M+ is estimating is that model unique to that class. So here I've got 4 items for a model for class 1. It's going to assume they're independent by default. Like our model parameterization says, it's just going to estimate the item threshold, which is the 1 minus the item difficulty, or -1 times the item difficulty, so the flip of it here. And actually here, these thresholds, this is where GitHub Copilot doesn't quite work out well for me here, but this is threshold, the first threshold for all of the items in class 2. So going back to that, if you put a model in the same, basically copy and paste the model into each, what this is going to do is give class-specific parameters to each of these models, right? That's how M+ is functioning. Finally, we may need some output. In this case, what I'm wanting is for each person, we want the probability a person falls into each class. That is what they call C probabilities, class probabilities. We're going to save it in an examineests.dat file, and the format is a floating point number, 10 digits before the decimal and 5 digits after. That's what that format statement is. Any questions on M+ here?
Yes, so in this case, that file C probabilities will have as columns as people we have the sample size with 2 columns with probes for each class, for each subject.
Almost. You would think that's the case, but M+ throws in some additional information in there. But I'll show it to you once we estimate this. But yes, there will be a probability for each class, and then there's some auxiliary other parts. But that's the one thing that we're most interested is the probability for each class, definitely.
Great, thank you.
Thank you, Vladimir. Other questions on M+ here?
Yeah, I have a question.
Yeah, Alfonso.
So in estimation, will the algorithm sort of, since it doesn't know what class you're in, will it assume you're in all of them? Sort of like the EM algorithm part that we talked about a couple weeks back. And then at the end, it'll do that C probabilities part where it actually fixes it?
No, so in this case, the C probabilities, the probability each person is within each class is actually estimated throughout the algorithm itself. And actually, this is there's multiple versions of the algorithm. In the EM algorithm, that's what happens. And M+ actually uses EM, quasi-Newton, and Fisher scoring. Fisher scoring I never talked about in class, but it iterates between the 3 depending on how fast it's converging. But under EM, remember an EM in IRT, the E step gives you an estimated theta, a mean, right? In the EM algorithm for the latent class or a mixture model, the E step gives you those C probabilities, the probability of persons in each class. That's the analogous quantity in latent class to psychometrics. So in the E step, in each iteration, we actually have this set of probabilities already. It's just that when the algorithm is deemed to have converged, we output what the endpoint of those probabilities happen to be. Does that help a little bit, Alfonso?
Yeah, thank you.
Great. Any other questions right now?
So I have a question.
Yes.
How we assign like 2 factors or 2 thetas instead of 1 here? In the code,
So we don't have theta in this model here. We have two classes, right? Is that weird?
yeah, if we are believing that there are multidimensional models, I believe so. How could we edit this code to fit with two factors instead of one?
Well, that's an interesting question. Are the factors classes or are they continuous traits? Because if you think about it, what's latent here is one categorical latent variable that has two levels, right? So you're saying, do we need another categorical latent variable? Is that what you're thinking, offhand?
No, I'm trying to reflect that on like multidimensional tests. For example, if we
okay.
are testing two dimensions and a math test, how can we assign that? And
Hold your question till the end, because I'm going to show
Okay.
more of that then. But for right now, we don't even have an assumption that there is a continuous trait at all in these data. Okay? Which is
Yep.
really weird. It's counter to everything we've done up to this point, particularly in any psychometrics, right? But this is what's happening. Okay?
Yep. Thank you.
Thank you. But hold that question because we will come back to it. Other questions?
Here we are using regular maximum likelihood, right?
Yes. Well, if you want to go with the framework that we described it last time, we are actually using marginal maximum likelihood, and that's because this sum right here marginalizes across the latent classes. So that's what that is right there. But yes, it's maximum likelihood. Does that make sense? Marginal maximum likelihood, but does that fit with what you're asking?
Yes, that helps. Thank you.
Perfect. Anybody else? All right, it's 1:50 and I've got lots of material left, so let's take a break. How's that sound? 1:53 actually. Want to take 10 minutes? Come back at a little bit after 2? Okay? All right. I'm going to have the video off and the... All right, welcome back. Here we go again. So this was our latent class analysis setup. I was working on the M plus syntax here. Now, M plus, I think we used it a little bit before, or I showed it a little bit in class. Today I don't have an example that runs M plus through R, but there is a package in R called M plus automation. You may have heard of before. Let's see if I can find that. I found it to be semi-useful in running M plus from R, so when you try your homework, I would suggest that you start looking there. But for me, what I'm just going to do, since I'm on a Linux device, I don't really have a graphical user interface for M+. This is going to be similar to what you have on a Tainer. But you see I have my file right here. I'm in the folder of where all the files are. So I created the brand new terminal window using ZSH. ZSH is like a shell scripting language. And I just have to type M plus and the name of the input file. The input file ends in .inp, so this is lca example.inp. I hit run. It goes really fast for these data because there's only 144 observations and only 4 classes. So what I'm going to do is I'm going to jump between my slides and the M plus output file themselves. The slides I have output examples, but those are more placeholders than anything else. But this is what we're going to be looking for in the M plus output. All right, there's a proportion of people in each class. That's our A to C. All right, so that's our sample information. We are also going to be looking for item information, so the probability of a correct response from examinees in each class. And we're going to look for the examinee information, the posterior probability of each person being in each class. Stop me if you have questions, okay? Start throwing M plus output at us here. All right, first thing we need to look at is looking for A to C. Turns out there's a section of M plus output that starts with this label: final class counts and proportions for the latent classes based on the estimated model. All right, this needs an explanation. Okay? So, let me get back to that. Let's just look at the M plus output first, okay? You can see in my Visual Studio window here, this output is, how do we say, voluminous, huge, lots of stuff here. Let me just show you what I have. Again, we're using maximum likelihood. In this case, it's Robust maximum likelihood, I'm not aware that there's a big difference in that. Here at the top part of the model, it actually gives you the univariate proportions and counts for categorical variables. So this is for every time you have categorical data. It's a data check. It basically tells you the proportion of people in each category. But the thing to remember here, in our data that we have given to M+, it's ones and zeros, but M+ categorizes them where the low number is actually a 1. Right? So category 1 represents a 0 in our data. Category 2 represents a 1. Kind of an annoying part, but that's what happens. The next section of the output. Random starts results rank from best to worst log likelihood values. Now, this is the part that I was telling you about where it basically ran 100 of the same models. This is the likelihood that you see all this number here. I have this negative 331.764. That's our log likelihood value. And you can see there's a ton of models here run. In fact, maybe that's all 100. I can't quite tell. It looks like it is. It's a lot there, right? That's a good sign. What that means is we have converging evidence that we found the global maximum. A not a good sign would be where you have one value that has the largest, the maximum, and the rest aren't that. That means you may have just found yet another local minimum, really, is what we call those peaks, those other peaks that are below the maximum. So this is good. Where you start to see local minima, more complicated models is really what happens. So the more complicated our model, the more likely it is it happens. M+ will warn you right here. It'll say, if it's bad, it'll say the log likelihood has not been replicated. There's a big paragraph that tells you. Here, this is good. It still wants us to rerun with at least twice the random starts. M+, I did 100 times. Come on now. That's kind of a... ChatGPT isn't running M+ output here. Topic for another day. All right. M+, you're used to seeing model fit information if you've seen this before. Number of free parameters, 9. I'm going to count those for you real quick. Remember, we have 4 items, right? Each item has a item difficulty or an item threshold. But that's multiplied by 2 classes. So that makes 8 of the parameters. And the 9th one is the proportion of people being in one of our classes. Remember, there's 2 proportions, but they sum to 1, so we only have to estimate one of them. How are we doing with that? Okay so far? Thanks for the thumbs up. Appreciate it. Probably should have... Now I'm sitting here. I'll make sure I can see the chat window in case anybody wants to throw a note in there. There we go. Okay, so again, we get our log likelihood. We can even correct it with MLR. The log likelihood, as you know, is the basis for AIC and BIC and sample size adjusted BIC. We're going to use those to figure out which model fits best when we fit multiple models. The chi-square test of model fit, you've seen this before when we talked about limited versus full information model fit. This is a full information model fit statistic, but we can use it because we only have 4 response patterns, and that's pretty... We have data in all of the 16, although we don't exactly have, 5 or more people in each. Let's go right here. Here's our data. You'll see there's one observation in a couple of these cells, but generally speaking, we've got pretty good data here. Most of the time, when you have lots of data, when you have lots of items, it won't even show this output to you. It'll just hide it from you altogether. Finally, we get into our model parameters. And this is weird because you'll see 3 probabilities here, right? The one to worry about the most is this one. Final class counts and proportions for the latent classes based on the estimated model. This is the model parameter that I described as being our eta parameter. And what that tells us is that 58% of people, or 58.656, are in latent class 1. Right? So if I go back to this right here, latent class 1 has the bulk of people, 41% is in latent class 2. Now, we don't know if latent class 1 or latent class 2 what those represent, but we just know 58% in one, 41%, 42% in the other. We'll figure out what the classes mean in just a moment. it does other things with these numbers that I'm not always pleased with. So I ignore these parts altogether. In fact, I'm not even going to give them the time of day to talk about. In fact, why we look here for the probability is in our model itself, remember our parameterization that I've described to you and the parameterization that you see in most of the measurement model or most of the literature on this keeps this parameter as a probability. Right? So in the m plus output, like to look for probability. But if you scroll on down the m plus output a bit more, you'll find that you see this, categorical latent variables, and the mean of it is 0.350. What the heck is that, you may be asking? Right? Turns out, m plus takes the log of the probability and models it. And that's what this is right here, log of the probability. But what it models, because there's two probabilities, it sets one of the log probabilities to 0, and another log probability is estimated here. So it estimated this as 0.350. It calls it a categorical latent variable mean. I guess technically it could be a mean of a categorical distribution. I really want to add R here. I need an R terminal. What I was going to do was basically go and show you where this came from. If I took exp of 0.350 and divided it by exp of that same number, 0.350 plus exp of 0, because that is the second latent class mean, I come up with the proportion 0.586. That is the same proportion that you see in our latent class model counts right here. Right? So what m plus is estimating and what it's trying to report as a proportion are two different things. Slightly change a little bit, but why m plus estimates a continuous parameter is because sometimes when you go and build a latent class model, you want to go and put what we call class-specific covariates in. So maybe there's a set of data that you have about people that would help describe why they're in a class, like maybe students who were in accelerated program were more likely to have the high performing class or something along those lines. But any questions on that so far? It's a lot, isn't it? Get used to seeing lots of output. Okay. Next, one other thing I wanted to note, it shows up down below, it talks about classification quality, and it defines something called entropy. That is something we'll use to describe how separable classes are. And I'll talk about that in just a few slides as well, too. Most of this other stuff is just irrelevant tangential information no one really cares about. But finally, the item parameters that we need to look for are here. And here what we end up estimating, remember, m plus estimates a threshold for each item. That's a logit transform probability, right? So this is like estimating for item 1 here, for U1. This is the log odds of an incorrect response. Remember, the threshold is like the probability of a 0 transform. The difficulty would be -1 times this. So this is the log odds of an incorrect response. And if we wanted to convert this to a probability of an incorrect response, we could take exp of that number, -1.117, and divide it by 1 plus exp of that same number. And now what we get with that probability is the probability of an incorrect response is 0.24. So if we were to actually go and take the complement of that, do this, we see the probability of a correct response is actually 0.753. Small random trivia note, if I just change the sign of this, multiplied it by -1, I still get that same number. So threshold and difficulty are sort of -1 times each other in this case. Cool? So what we need to do is determine what does each class look like, right? So what I could do is I could calculate a probability of a correct response for each of these numbers. And I could calculate a probability of a correct response for, oh boy, each of these other numbers. It turns out m plus, if you scroll down enough, actually does give you those probabilities right here. So results in probability scale, That first number, 0.753, that is what I just created. That's category 2. So remember, category 2 is where we have our correct responses. So class 1 on item 1, probability 0.753 of a correct response for class 1. Now let's look at class 2 for item 1. Probability is 0.209. So just looking at item 1, we'd say people in class 1 have a much higher probability of answering the item correctly than people in class 2. Let's see if that trend continues, shall we? What we're trying to do here is describe what each class means. In class 1, for item 2, 0.78 chance of answering it correctly versus 0.06. So still that trend continues, and so on throughout. So, go back to my slides here real quick. There's the probabilities I was just mentioning. We can actually plot this. Here I used Excel to plot this many years ago, but I'll just show you this right here. But here you can see this is the class-specific probability for class 1 for each item, and the class-specific probability for class 2 for each item. What sticks out to you from that plot?
The first class had the highest probability at each item to have a correct response
Yes.
for each one.
So, what will we call this class? What does it mean to be in class 1? Pardon my mute button for just a moment. So what do you think? What does it mean? What do we call people in class 1?
Those are the students who master the content.
That is what McCready and Dayton would call them. I might call them students who have a higher chance of answering it correctly. But let's think about what that means. That means probably students who have higher abilities, if we were to measure an IRT model, than students who are in class 2, right? What do you think? Anybody want to argue with that point? I like the argument. I welcome the argument. I mean, who likes arguments? But let's make it a philosophical discussion, something like that. Not like a hostile thing. Is that really mastery?
Depends on your definition of mastery. But I feel like this also shows us that there's less probability for that problem or item 3.
Yeah.
For item 3 is probably one of the harder items to answer.
Correct.
So that's something else you can get out of it.
That's right. Actually, if you look at, Jacinta, thank you for that comment, actually, because if you look at the probabilities overall, this is the probability of anybody, regardless of class, answering each item correctly, right here. And let's take a look at item 3. The proportion of people answering item 3 correctly is 0.261. So only 26% of students in the sample answered item 3 correctly overall. And when you look at that plot, I have a different version of the plot right here, you can see that 0.26 is right in the middle there, right? Turns out, yeah, that is a more difficult item. And as you get into these models more, what you're going to actually realize is that some of our marginal parameters, like this 0.261 right here, what if I told you I could probably recreate where that came from? Are you ready? Let's do this. Let's take the proportion of people in each class. You know, and I have it summarized in my slides rather than fighting with M plus output. Come on. Why can't I get to Quarto preview? Come on. There we go. All right. So we have 0.58656. That's the proportion of people in class 1. Now take a look at the proportion of people of class 1 who answered it correctly, 0.432. So we could actually say, if we multiplied 0.432 by 0.5856 by the proportion of people in that class, and we add to it the proportion of people in class 2, 0.41344, times the proportion of people who answered it correctly in class 2, 0.018, we end up with a probability of 0.26, and if we go back to that output, you'll note that that is just about what the probability is marginally. So what am I telling you? What this is telling us is basically the mixture, right? Why we observed 26% correct responses for this item is that people in class 1 who accounted for 58% of our data had a 43% chance of answering it correctly, whereas people in class 2, which accounted for 41.3% of our data, had only a 1.8% chance of answering it correctly. So when we get the weighted average of the two, we end up with what the actual number is, which shows you sort of how the connection between model parameters and the data sort of get fit together. Does that make sense? Any questions on that thought? Nah? Cool? Should I keep moving on? Let's keep moving on. All right. Okay, so that's it. That's the model. That's the model. Now we do all the other stuff that we do in psychometrics with it, though. We need to know if the model fits the data, right? By the way, you like this model? What do you think of it?
I think that is useful, but the thing is how to interpret those classes. that can take a lot of work because you can say whatever you want to say based on those results.
That's right. I mean, you look at our picture here. I don't know about you, but I wouldn't use the word mastery to describe somebody who has only a 43% chance of answering an item correctly, right? Even though it's a hard item, you know, mastery, it's a label that we attach to it, right? So
That could also be, I'm thinking you would also want to maybe investigate that item to see if it's aligned with what it's supposed to be aligned with, if it, like all of those sort of things, it could be a sign of something else as well.
good point.
But
We're doing psychometrics here, even though we're not using what we would traditionally think a psychometric model would be. But everything we consider when it comes to building an assessment matters here too. Like, for instance, do we have one dimension or two? Right? Are classes really one dimension or two? That's another thing that I mentioned at the beginning of class. It's hard to define what dimensionality means. Here's what a key part, right? So if this item is not aligned with the others, yeah, I could see this being sort of a weird combination of models. So, yeah.
Jonathan,
Mhm.
now that you have the picture there, in this case we have 4 items. Is there some kind of minimum number of items that we should have to try to use these models?
Great question.
Or as much as possible is like the rule?
The same, basically the minimum numbers that you have in the one class model. So if we were to fit a psychometric model with one class, if we could estimate it with one class, then in theory this model should be identified for more than one class. Now, the in theory part of that is, again, remember that mixing proportion. It may be the case that we have a hard time putting people into multiple classes, so we get a small proportion in another one. But generally speaking, from a pure latent class model perspective, we could actually run this with one item, believe it or not. It's not a good idea. Actually, with binary items, I may not be able to. I think continuous items, I think with binary we need 2, with continuous we need 1. Point being, not a great idea. When it comes to interpreting this, in particular interpreting this like we would with latent variables like abilities or personality traits or some other type of quantity about a person, then the measurement model perspective still applies. So if we were to turn this into a mixture IRT model, for each class we have the same minimum number of items we did in an IRT model to make sense of it too. So in an IRT model I keep telling you 3 per factor. That's not entirely correct, but it's close enough. So you'd need 3 items per class to estimate an IRT model for this. Does that help, Vladimir?
Yes, of course. Thank you.
Thank you. Other questions? Okay. If you're like me, when you learn about mixtures, you're like, oh, these are amazing. But then as you start to learn even more of them, you're like, oh, these are crazy. So let's talk about model fit first, and we'll talk about some of the problems with mixtures real quick. We have a really hard time assessing model fit, as you would imagine. But it turns out we will use very familiar looking model fit measures to do that. So some of the stuff we've taught before in class, we can talk about model-based hypothesis tests. In our case, we can do this. In many cases with data, we can't. But this would be called full information absolute fit. We could also come up with information criteria. This is a LaTeX. This should be a separate bullet. But we can come up with information criteria for relative fit. We could also come up with measures of distributional characteristics. I would call this limited information fit as well too. So that limited information fit still is there. We don't call it M2 as much, mainly because I don't know of anybody who's put it there. We could use M2 if somebody wanted to construct it. We could even do that, but we don't. And then finally, I mentioned before entropy. Entropy is a measure of how much overlap in the distributions there are for the classes. Some people use that for model fit, but I caution you against that. It is actually, entropy is very much like what we would call reliability, and it depends on the model fitting well. It's not an index of model fit. All right? If the model fits well, it talks about how well the classes are separable. So let's dive into this. This is our latent class model right here. The model itself will always depend, or model fit always depends on sort of coming up with predicted quantities based on this latent class model. So literally with this model and with our probabilities that we got from M+, with our model output here, for each possible response pattern, we could come up with what our model suggests the probability a person will have that response pattern happens to be. And that's exactly, if you looked at this picture from McCready and Dayton, actually this is from Bartholomew and Knott, this, let's see here, nope, this is not it. This is the posterior probability of mastery. But what you can end up seeing here, this expected frequency that you see here, what that comes from is our model itself. So if we plug in all of our model parameters, and then we go back and we look at the y's, right? The actual values of y. So this, in this case, the first response pattern is 1, 1, 1, 1. So here, if we plug in 1, 1, 1, 1 for y, and we have all the other parameters, what this equation gives us is the probability someone, a person at large, has a response pattern of 1, 1, 1, 1. That probability, multiplied by the frequency of, or basically multiplied by our sample size, is our expected frequency for the data, right? So this model itself we can use to come up with a expected response pattern probability. We can do that with any response pattern. M+ actually gives you this information using the Tech 10 output option. So if we go all the way down to the bottom of the output, you'll see this information right here. Here is our observed frequency for each response pattern. Here is our estimated frequency. And it comes up with a chi-square for it, right? So this is what we would call full information model fit. Now we can only do it because we have 4 response patterns, right? But remember when we introduced M2 and limited information model fit? Do you remember that way back when? Months ago? A month ago? We had to use limited information because when we have lots of binary items, we have lots of sparse response patterns, right? The target distribution is the same. Well, it turns out the target distribution for this model is the same as the target distribution for the IRT model. Why do I mean that, right? So remember, what we're after is a multivariate distribution of Bernoulli variables. Okay? That's the same. Whether you use IRT or whether you use latent class analysis, it's the same. It's the same target. We have to fit that data well to make it work. So if you think about we're doing a latent class analysis, it's a lot harder because each person is just assigned to a class, and based on that class, we get a likelihood contribution. Whereas in IRT, each person has a theta, and that theta has, fine-grained differences between people more than the classes give us. So in many ways, this is like an approximation to the IRT model, but we're still using the same types of model fit to build, to understand whether it fits data. Am I making any sense? I hope so. All right, I'll take your word for it. Any questions? No questions. Okay, so Tech 10 gives you this output, but this output's actually summarized at the top of our output here, the chi-squared test of model fit. Here we have 6 degrees of freedom. The degrees of freedom comes from the number of response patterns, 16, minus the number of parameters. We had 9 parameters estimated. So 16 minus 9 is 7, minus 1. So response patterns minus parameters minus 1 gives you degrees of freedom. In our case, we can tell that this chi-square value gives us a p-value of 0.1494. By the way, this other value, the likelihood ratio chi-square, is asymptotically equivalent, meaning as the sample size gets really large, they should give you the same result. And this is our Pearson formula right here. I'm showing you all that. This is our likelihood ratio chi-square formula. You may have seen that otherwise. I just wanted to put that together, put that in there for you. So what does this tell us? Well, these are comparing, again, the frequency we observed with the frequency we expected. So if the chi-square is not significant, it means our expected frequency matches our observed frequency. Or, another way of putting that, the model fits. Right? So if it's not significant, the model fits. If the chi-square is significant, then our expected frequency does not match our observed frequency, and the model does not fit. So here this would tell us the model fits the data. Not bad, right? It should fit. We only have 4 items, but that's what's happening. Questions on that?
So, just to be clear, from the response pattern, frequency, and chi-square contributions table, we are taking that difference between the observed and estimated numbers for each response pattern there. Then we have the chi-square value, summing those differences.
Correct.
But those differences are not displayed there, right? For example, for the first pattern, we have 15 minus 14.
Right.
But the difference is not
Here,
there, right?
this column, the chi-square Pearson column, is effectively observed minus expected. Let's go back to the formula. It is observed minus expected squared over expected for that cell itself.
Oh, for each one, okay.
That's right. Mm-hmm.
Okay, great.
So each
Thank
one,
you.
this column here in the Tech 10 output tells us each cell's contribution to the overall chi-square number that we sum to. And this column, chi-square
okay.
Pearson, is the first one. Chi-square contribution chi-square contribution likelihood is the second.
Oh, okay. Awesome. Thank you, Yonada.
Thank you. Ahmed, I see you may have a question.
Yeah, I'm not sure whether this is relative to that or not, but in other classes we keep talking about the true positive rate and true negative rate and those stuff. As we are doing prediction here, this is like an overall error rate. So could we break it down into true positive or false positive or something like this? Or we don't do that here?
In this case, we don't. But I will say that that classification itself, if we were to simulate data, and we have a true, so we know which class people are in, right? Then we could take our model and basically say, if the model were correct, what's our true positive for classification rate? What's our true negative for classification rate? Does that make sense? Like for each person, are you in class 1 versus class 2, right?
Yeah, so is this strategy could evaluate the model fit in this case?
In that case, no. Actually, it turns out that idea of true positive and true negative is actually related to classification quality. But it turns out you can have a very poorly fitting model that classifies people. They just classify them very wrong, right? So model fit for us has to describe whether or not our model parameters do a decent job of describing our observed data. That is where model fit is going. And if they do a decent job of describing the observed data, then we can talk about classification quality, like true positive and true negative. But that's only if we fit the data well. If we don't fit the data well, it doesn't make any sense to talk about classification quality, because we're sort of in a fantasy. The model is sort of out there in a dream, right? It's not real. And if it doesn't have any projection onto data, then we're just dreaming up which group people might be in without any empirical evidence to suggest it relates to how they respond. Does that make sense?
Yeah, yeah.
So interestingly, I'm glad you brought that up, because you've heard about true positive and true negative and things like this, and you may have heard about that perhaps in some of the machine learning literature or perhaps in some machine learning classes.
Yeah, but in the context of that they are doing prediction models, not inference models, so it's different context.
People,
but, I wonder if this could be reflected in
it turns out there's an equivalence to these types of models with a lot of the machine learning architecture. If you think about a neural network, each node of the neural network is like an on-off switch. We have a one-node neural network here, right? So what I'm talking about with this is some of the concepts from psychometrics that we understand, that we worry about, doesn't always apply in other fields, but this is one of them, model fit. Nobody talks about model fit in the classification sense, but that's incredibly important. So,
yeah, I can see the connection now. So,
yeah, it's very interesting how it works. When we get to next week, if you ask me that question again, I can show you, because diagnostic models are, again, latent class models. But I can show you, but there's some like layers of how complicated models get. And some basic models, when we fit them, will have higher entropy but worse model fit. So what we're saying by that is, if we believe this model, it's a lot, the higher, in this case, entropy is actually backwards. It should, M plus rotates it. The maximum entropy in M plus is 1. I called this relative entropy in my slides going on. But anyway, long story short, what that really means is, if a model doesn't describe the data well, sometimes we get even better classification out of it. But those classifications, like if we truly could observe people, may be false, right? So it's this odd parallel. The closest I would describe it to is saying, what's the reliability of your data, right? Like an assessment. When we talk about reliability of an assessment, sometimes we talk about conditional standard error of measurement in IRT, right? But if every one of those versions of reliability or conditional standard error of measurement implies some type of structure to the data, even the classic sense, right? Spearman-Brown assumes parallel items, whereas the coefficient alpha assumes tau equivalent items. Pardon me, I'm blanking on everything here. But all of that depends on the model fitting. Because we could always calculate Spearman-Brown and we can always calculate alpha, but if our model, like if we fit a unidimensional model, but we really should have had 2 dimensions, what's alpha mean? Nothing, right? It doesn't tell us anything really. So, anyway, model fit comes first. Reliability or classification accuracy is conditional on model fit. That's where I'm going with it.
Yes.
So
Thank you, sir.
good question. All right, any other questions while we're here? I see no questions. All right. One thing you remember, though, is that there's problems with chi-square, right? This is our full information model fit. It's the optimal statistic, but the problem is, we had 16 possible response patterns. If we had 20 variables, we would have 1,048,576 response patterns. We'd have no data in most of those, right? So model fit gets bad. What we can do instead, where I describe this in other places, we can do model comparison, but we're not. Let me come back to model comparison. I really should have changed this. Instead, we can do what's limited information versions of model fit. Remember, in limited information, we looked at fit to, like M2 looks at fit to marginal contingency tables and bivariate contingency tables. Remember that? Turns out Tech 10 and M plus does the same thing. For marginal contingency tables, we have to come up with what the expected proportion in each cell would be. I just did that based on the model. But it turns out our marginal model, remember when the first thing I calculated here, the proportion of people answering item 3 correct, I guess that was the second thing, right, was 0.26, right? This line right here that I'm highlighting is from our model. So that's our model implied mean of the item. Right? We could use that and come up with some fit statistic like a root mean squared error for each mean. However, fitting to the mean is really kind of bad because we're not going to misfit the mean. So long as each item each class has a very mean specific item parameter. Remember, a threshold is a mean, it's just transformed. So each class we're estimating effectively a mean of an item per class. We're going to recover the means well. We have all those means saturated. And that's what ends up happening. If you go down to the Tech 10 output, in the univariate model fit information, H0 is our model, H1 is our data. Okay? So here, our model is suggesting this be the mean for each variable. And remember, the mean is the probability of a correct response is for category 2. These two numbers sum to 1. But you'll see here our model and our data fit perfectly, right? By the way, we may talk about this a bit. I hinted at this in model fit before. This is what the diagnostic model literature calls RMSEA. It's not RMSEA as we know it in structural equation modeling, and it's useless, right? We will almost always fit the item mean. The only way that we won't is if we make a constraint on that mean parameter, and why would we want to do that in the first place? So univariate model fit, kind of stupid. I'll just say it. I can say that word, right? Irrelevant, pointless, pointless. Bivariate model fit is what's important. So what we have here are 4 lines. We have variable 1 and variable 2. These are the 4 cells of the contingency table between them. Right? So if we make a 2 by 2 table, correct, incorrect for item 1, correct, incorrect for item 2, you can see which each of those proportions are. And again, using our model, we could actually come up with what the probability for any given 2 cells would be. And that's the product of the item parameters times our class-specific proportion. So here, you can see each of these values. You can see for each pair of items a Pearson chi-square. So you could tell for a pair of items from this whether that pair, the model fits that pair well. And then at the bottom it sums those overall bivariate Pearson chi-square and overall likelihood ratio chi-square together. And this is like what M2 gives you. It's an overall test statistic. However, it doesn't have a p-value for it. The literature in M2 showed how to find a p-value for limited information fit for it. Actually, M2 combines univariate and bivariate, but you saw the univariate being at 0 because it fits univariate perfectly. But when I look at this, right, I see no pair of items having a very large chi-square, one that would be statistically significant. So when I look at this and I see all pairs of items with fairly good fitting data, I would say the model fit these data pretty well. That's what I'm coming from here. So in an absolute sense, we saw that with the model chi-square, the one at the top where we had all 16 profiles. And now from the bivariate chi-square, we're also seeing that. Any questions on any of this? Moving on then. Let me go back. The other thing we can look at, we can come up with information criteria. Right? So remember our likelihood value. This is our likelihood for our latent class model. I just took our single person's likelihood and took the product across our sample. That's our sample likelihood function. We can take the log of that right here. One thing I will note, actually, give me one moment to note it. I just need a second. The voice is holding up well. The nose is starting to fail. So just going to take a second there. Here, one note I have is calculating this if you're trying to do this at home, because why not? And by the way, I encourage everybody to try to estimate things at home. Why not, right? That's how you learn stuff. The log of a sum is not equal to the sum of the logs. So what that means is you cannot easily pass this log through the sum that you see in here. So you've got to worry about that with numerical stability, by the way. But leaving that aside, once we have the log likelihood, we can then use it to form our AIC, where Q is the number of parameters, or our BIC, which weights in Q and our sample size, and then M plus lists the sample size adjusted BIC, which I'm not entirely sure what the formula is on that. But information criteria are what we use to determine how many classes we have in our data, generally speaking. So let me move forward. Come back there. So basically, if we were to estimate multiple models, 2 classes, 3 classes, 4 classes, and so forth, with 4 items, we really can't get that many. What we would do is look at model fit. Do you want me to try to fit a 3-class model and see how it works? Anybody?
Yes, thank you.
All right. You know what this means, right? Thank you, Vladimir. I'm going to make you the scapegoat here. That means I'm going to follow Vladimir's request, but it's going to fail because I didn't plan this ahead of time. And then it'll just be Vladimir's fault. Right, Vladimir? I'm just kidding. Sarcasm.
Yeah.
It's
Yeah,
not Vladimir's fault.
Thank you.
It's my fault. I'm responsible. But that being said, here. I believe, let's see here. We are estimating 5 more parameters. Let's talk about this degrees of freedom. Last model had 6 degrees of freedom, right? This model, we add in how many more parameters? 5. We have 4 probabilities, one for each item, and we have 1 additional class parameter. So that's 5. So we should have 1 degree of freedom left, which means we should be able to estimate it. Let's take a look. All right, it ran. Okay. Let's take a look at our output. First thing, let's look and see if we should believe it. Turns out, log likelihood has been repeated, so I believe that we should be able to repeat it. One thing it does warn us, though, is 1 or more logits got extreme, and we had to fix it to stabilize model information. This is the case where I'm going to guess that at least one of those classes had very few people in it. Why I'm guessing that is, think of it this way. This logit, the probability, this is the proportion of people who are answering an item correct. If all of a sudden we have a class that has 0 people in it, remember the mean formula is divided by n, it's not going to be able to be estimated. Similarly, if everybody in that class answered the item correct or incorrect, we can't estimate it, right? Because the likelihood's undefined, right? So we have a problem. But it looks like we did get it to estimate. The model fit is somehow worse. It doesn't fit the data absolutely, which is interesting, right? We've just increased the complexity, but the fit got a little bit worse. But now let's take a look at our proportions. Actually, we have sufficient numbers of people in each class. 40% in the first, 25 in the second, 35 in the third. And let's take a look at these estimates. Ah, there we go. We can tell the problems right now, right? Latent class 1, item 2, very small negative number, which means really everybody in class 1 answered item 2 correct. That's what that's mentioning right here. Remember, because threshold is the opposite of a difficulty. There we go. And now in class 3, everyone in class 3 answered item 3 and item 4 incorrectly. That's what that's telling us. And if we were to go down to the results and probability scale, we'd see just that. Here's the 100% of people answering correctly in for item 2. And here's 0% for item 4 and 0% for item 3 under the class 3. Now, what do the classes mean? Gets harder with 3 classes, right? But 0.86, 1, 0.44, 0.752. It looks like this first class is still the people who are mastering or have the highest performance. But then let's take a look item by item. Item 1, probability correct response 0.83 for class 1, 0.525. So they're lower, 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 and lower. And then if we look at class 3, even lower, even lower, even lower, and even lower. What we've just done, dare I say, because the class probabilities are monotone and decreasing across the classes. Class 1 is our most highest ability students. Class 2 is our students who are somewhere below that. We don't know exactly how much lower. And class 3 are people who are even below that. So, see what I did? Now, should we choose class 2 or class 3? I think we already know the answer based on the absolute fit, but let's look at the relative fit real quick. This is class 3. This is class 2. So AIC and BIC is what I'm looking for here. In class 2, the AIC was 681. In class 3, AIC was 686. So we want the lower number, in this case, class 2. The 2 class wins for AIC. For BIC, 728 for 3 classes, 708 for 2 classes. So BIC suggests 2 classes. And if we even take M plus's number here, sample size adjusted, 679 versus 683. So all 3 suggest that we should use the 2 class model. Cool?
Yes, thank you.
Thank you. I'll do one other thing. I'm just curious about model fits. Let's go back down to the Tech 10. Again, the univariate fit is almost always perfect as long as you have item parameters for the mean that vary by class without constraint. But now look at the overall Pearson chi-square is actually better. So what basically this is telling us is we've got better fit to the contingency tables, the two-way tables. Now you may have noticed we had now a significant chi-square, but that was because our degrees of freedom were so much lower. Our chi-square overall, like the actual chi-square itself, not the test statistic, was smaller, 3.994 versus 9.459. So in many ways, in an absolute sense, this model is getting closer to it. It just turned out that because our degrees of freedom is smaller, our p-value is very close to 0.05. All right. Any thoughts or questions on this model?
Quick question.
Yeah.
Should we drop items with only zeros or ones at this stage of the analysis?
No, we shouldn't. We should never really drop anything like that. If we sometimes may have to, depending on the motivation. But here, if you think about what it means, again, let's go back to those probabilities, right? It just means the model wants the class 1 to have everybody with the highest ability in it. And that means everybody's going to answer the item right. That's meaningful, right? Just because the logit value of that is undefined, right? We can't estimate the logit of the threshold. Doesn't mean that it's not meaningful. In fact, if we were to if we were to estimate this model not in logits, not with thresholds, if we only have the item probability parameters, we would be able to find the likelihood. We would be able to estimate it at 1. Wouldn't have a standard error, but it would be at 1, right? So, hope that answers the question.
Great. Yes, thank you.
Thank you. Any other questions? Okay, let's talk about entropy real quick. For this, we need to look at each person's classification. And actually, I just realized that I copied and pasted the 3-class model, so I need to rerun the 2-class. This is the output file from M+ for the classification. What it contains in it is the data that was observed for each observation. So this first row is person 1. That person had answered all 4 items correctly, and in fact, if we look at the data, you'll see a 1111 for person 1 at the top here. So the first 4 entries in this are 1111, that's the person's data. Then we get the probability there in each class. So probability of class 1, 0.9999995. Probability of class 2, 0.000005. And then finally, the last number is which class has the highest probability. In this case, class 1. So these we would call actually EAP estimates. These are analogous to the EAP estimates of theta. They are the expected value for the categorical distribution for each class. And each person has that, right? But unlike theta, these are categorical distributions, which this probability, since there's two classes, we only need one probability. It not only tells us which class a person's in, right? So if it's bigger than 0.5, a person is most likely in class 1. If it's less than 0.5, a person's most likely in class 2, right? So it tells us which direction, which class they're in. But the closer it gets to 1 or the closer it gets to 0, it talks about how certain our classification is, right? So we're very certain this person is in class 1. And if we go down to the end of this file, we'd see we were very certain this person, the last people, the person that had 4 zeros, was in class 2. Right? And then perhaps somewhere in between, we have some classes that are a little bit less certain about. But what I'm painting a picture for you here is this is our latent variable, but it combines both the location, so which class is most preferred, and the variance, like how certain we are in our classification, into one number. And that's like thinking about that blows like everybody's heads up in educational measurement because they're used to having a mean and a standard deviation and everything being continuous. Both of these numbers contain both bits of information. Am I making some sense here? I don't know. I got to get moving though. Here's the thought. We can quantify how much uncertainty there is using this entropy formula. So in original latent class analysis, entropy was a number that measured how much classification uncertainty there was. Basically, it's an index of how close to 1 each person's probability is. And if we were to classify, if we were to look at this examining output file again, if we looked here and we saw that each person had a 1 for one class and a 0 for the other class for the probability, we would classify with complete certainty. And this entropy measure would turn out to be 0. Completely 0. If, however, the entropy, if we had the opposite, which was if each person had a 0.5 probability of each class, now we have no certainty at all. It's completely a coin flip as to whether a person's in class 1 versus class 2. And that would be the maximum value of entropy right here. And we can actually calculate what the maximum happens to be. We could just hypothetically say that, right? If we have C classes, we know that the most uncertain we're going to be is when each person has a probability of 1 over capital C for each class. That's the maximum entropy. So M+'s version of entropy actually uses the maximum and converts entropy to be a number between 0 and 1, meaning it's better to be closer to 1. I hate that they do that. Entropy in physics means sort of loss of information. Well, M+ calls this entropy. I would rather call it relative entropy. But that's just me. But the number of 0.754, it's closer to 1. What this tells us is that we have some pretty good classification certainty in our data. But that's all it's doing. It's describing how much certainty we have. And if we were to calculate a reliability measure, this would be highly related to that reliability. Reliability of classification in a sense. Or as Ahmed said, the true positive rate versus the true negative rate. Something along those lines. So entropy comes at the very end once we're assumed that once we know that we have a good model, and it tells us how much certainty we have in our classification. That's it. M+ used to put entropy up under information criteria, but thankfully they've moved it. Any questions? One, two, three. No questions. Yeah, question? Yes, please.
Yeah, it's not related with entropy, but I wonder that our model doesn't have alpha PC, which is examining information. So is it marginalized over alpha?
Yes. So this for each person, alpha, you notice, isn't in our model itself. In fact, we don't have an alpha anywhere. That's because the model itself, when we define the likelihood function, is defined in this way, and we've marginalized across it, just like what you said. There are other ways that we could express alpha in this model. We just chose not to do that. But this is the model itself it's one of the things actually, Akyung, that gets sort of confusing here. Notation in mixture models is not consistent and is actually when I was really into them, not that great. But it's almost impossible to clarify. But thank you for pointing that out. Alpha doesn't exist in our model, but that's because we've marginalized across it. It is part of our model, though. Does that answer your question?
Yes, thank you.
Thank you. Other questions? Okay. Well, let's talk about some more interesting models. I don't think latent class analysis is that interesting. It is interesting comparing why we have better fit and everything, but let's talk a little bit about how we put mixture models together. So remember, this is the formula for the finite mixture model. And literally anything you can put as a model in this class-specific likelihood itself. This is the distribution of a model. It could be an IRT model. It could be different IRT models. One class could be IRT and one class could be something completely different. You can do that. So long as you form a proper model and a proper distribution within class, you could specify that type of analysis. So a mixture IRT model is just that. Here, now we're going to condition on theta, right? So here, the mixture model, we're not describing the fully marginal data yet. We're conditioning it on a latent variable theta, but we can integrate across the classes, and now our class-specific model probability, y, this thing right here, is again a Bernoulli distribution, but that probability now comes from an IRT model where theta shows up and each class has a discrimination parameter and a difficulty parameter. Right. So this is how we do mixture IRT models. You will find mixture IRT models. People had used it, again, this is 15 years ago. People were using these to talk about multiple strategies, like people with different strategies answering items. I hated that. I think that was not supported by data. That's a claim that didn't have any relevance to what we do, at least that I could tell. So it was sort of been thrown away. But that being said, we can talk about different types of examinees. Let me show you. Would you like to see how we'd parameterize a mixture IRT model here?
Why not?
Why not? Rename this to class IRT. Okay. So here, what is our IRT model in M plus? We can estimate all of those. We can have theta by U1 through U4, U2 through U4, and I put the asterisk there because I want to estimate the discrimination for it. Then I would need to set the mean for theta in this class to 0. That's what the brackets do. They talk about a mean, and then I want to set the variance for theta to 1 in this class. So far, so good. And in class 2, we may want to do the same thing right here. However, maybe we want to estimate theta's mean. Why don't we do that? See if there's a group difference in thetas. Sound good? Should we try it? Let's see if this works. By the way, Vladimir, since it didn't blow up the last time, it's not your fault. This is my fault now. An error occurred. Of course it occurred, because I'm on the fly here. Theta in the by statement. Oh, that's right. When you're fitting this, what you need to do is define theta in the overall model, otherwise it won't know what to do with it. So here I'm just going to put my model specification of theta in, and then it overrides that for each of the other models. Nope, and there's still an error on it, of course. Oh, and I need algorithm equals integration. I need to integrate out theta. Let's see if that works. I think there's one more. No, it did. It's taking longer to run. It's a more complicated model. But now let's take a look at its output right here. First thing I want to look at is whether or not we got the same log likelihood. Now look, one log likelihood is negative 324.146. That's the highest. It was not replicated, so take a look. Warning, warning, warning. This is not good. Oh, also the degrees of freedom for this model are negative. It's not identified. It turns out with 4 items this is hard to do. What I can actually do a little bit better is do this, I think. This U1 to U4 at 1. I'll do this right here. Let me see if I can estimate just a mixture Roche model instead. George Engelhardt would tell me this is like a mixture 1 parameter model or something, I'm guessing, but that's fine. So I'm going to change code ever so slightly. Actually, I might just take those off too. Actually, before I do that, let me try one more thing. This is where class is crashing and burning, but hold on, it gets better. I promise. Let's try this one more time. I may have misspecified with the logits there. By the way, look at all these output files in the temporary sense. Those were all files that M+. Oh, I have a degree of freedom now. I don't know what I did before. It still didn't like that. We still didn't get the maximum log likelihood replicated. So it's dangerous to interpret this, but let's just do it anyway. You'll look, our model actually didn't fit the data. What? How'd that happen? But yeah, again, not better. Class 1 had 62%, Class 2 had 37%. What do our classes mean? Pardon me. Class 1, here are our, these are our loadings or discriminations. We see item 3 had a huge discrimination parameter and a huge threshold. Again, numerical stability is not good with these results. I wouldn't trust this model. But class 2 had negative discrimination parameters, which is even more interesting. They're not related to theta. And then the mean of theta was actually 5.7 standard deviations lower. So I would not interpret this information very well. I may try a mixture Roche model, but that's mixture IRT. Do you want me to try the mixture Roche model to see if it fits any better so we can do better interpretation? Anybody?
Of course, we are here.
You're here? Why waste time? Let's see if I can do it. I need to fix all these at 1 and estimate the variance. Do that. Do that. But in this case, I am estimating theta's mean for class 2. Like that. Now let's give this a try. And our output. Now, let's look and see, did we get the same? We did not get the same log likelihood. We got close, but not the same. So again, interpret this. Oh, it says best log likelihood has been replicated. Oh, okay. Better, I suppose. Worst model fit. But here it's a little bit easier. We can see the thresholds for each item. Right? Here's the thresholds for the first, these being first set, and the thresholds for the second set. Oh gosh, I did it wrong. Sorry, the thresholds are all equal. I need to actually separate them. So I need to estimate the thresholds separately. So this is the thing about M+. If you specify a model overall, but then it fixes the model parameters across the groups. Here I don't have any separate thresholds, which is not really a model I want. Let's see if it works any differently here. All right, now 320 again. It worked a little, and it still doesn't fit that well. Let's take a look at our values. Thresholds here are, what they are. Got some thresholds that went all crazy. Take a look at our theta estimate right here. You like a variance of 3,482. Ever seen that in a model before? Not going to work. So, mixture IRT for these data, we're below what really can get functioning, and that's actually because, think about it, we're trying to run an IRT model on 4 items, and then now with 2 different groups of people with 142 observations. That's widely optimistic, I would say. Wouldn't you? So, there you have it. All right. Other questions you might have? For me. No questions. So you know everything about mixtures. At least we started. Okay. For those of you who had a little bit of knowledge of mixtures before, this helped fill in some of the gaps that we didn't talk about. Maybe, hopefully. That's my hope.
I have one more question.
Yeah, please, Akim.
Yeah, in the model, the pi is just item difficulty.
Mm-hmm.
It's just so we don't estimate any parameters for that.
No, it is a parameter. That is an item difficulty parameter itself. So it is a model estimated parameter.
Oh, okay. Thank you.
Thank you for asking. So, homework this week. There's 2 features of homework, right? Apply just latent class models to your math data from the example data sets we've had. And then apply mixture IRT models to the same data and see what class solution you have. So you get some practice with 2 types of models. And then the third question is take M plus code and tell me what the model is for it. Give me the notation for the model from it. Sort of translate M plus backwards. That last skill is a hard one, as you just noticed. I'm sitting here trying to figure out what M plus is doing, but I want to tie model parameters to M plus with you, so I think that's important. The homework, I'm actually going to give you 2 weeks for it. I mentioned last week it was only going to be 1. I've changed the schedule around because we're going to stay on mixtures these next 2 weeks, so you get 2 weeks to do it. Evidently, Argon and IDAS aren't working today, so you won't be able to start today, but tomorrow morning at 8 o'clock they should be back online, if not before then. So hopefully that'll work for you. But that's it for me. Anything else from you today? Anything else you want to talk about? I'll take it as a no. Thanks for being here. I hope, sincerely, that I'm in person with you next week. Thanks for your patience with me. If this is another cold, I don't want to share it. So I hope the rationale was okay. And then I hope the Zoom instruction was at least sufficient for what you need to get you started. But in the meantime, Friday, office hours, 9 a.m. to 11 a.m. in the same Zoom room. I'm just going to be at home working instead of being on campus. I know tomorrow is the Linkless Legacy lecture with Mark Ricase, whose chapters from the book what we've been reading, so I encourage you to go at 3 p.m. I can't remember which room it's in, but at 3 p.m. tomorrow. And I think he's giving a workshop for students on standard setting, if I'm not mistaken. I don't remember where that is, but that's Friday, right? So thank you all for being here. Hope you can see Mark and everything. I think with my cold, I probably won't be able to make it tomorrow. But in the meantime, if you have questions, if you talk about anything that's related to anything in class, please don't hesitate to talk about it with class as well too. Anyway, nice to see you all. Hope you if you're not feeling well, hope you get better. if you are feeling well, hope you stay that way, and I hope to be in person next week. So take care, everybody. Thanks again.
Thank you, Jonathan, for the additional example.